Good afternoon, all. My name is Nick Samus. I serve as an adversary emulation engineer with the MITRE Corporation. I'm an aerospace safety engineer by background, turned cyber engineer by trade. I've spent my entire cybersecurity career in operational technology, primarily in industrial control systems, where I've worked to further cybersecurity capabilities into our civilization's critical infrastructure. In my current role, I seek to push the science of how cybersecurity is used for adversarial effect. My focus remains on operational technology, that is where computing and physical systems interact. I want to thank RSA for putting on a great conference this year. I'm excited to be speaking to you all today about increasing the resiliency of our space infrastructure by way of increased insight into 5G operations. This presentation will cover concepts that are paramount for an effective strategy as we look to monitor for cybersecurity implications in our 5G infrastructure. And I hope that the concepts will be useful for you to take away to your enterprise, be you a space operator or otherwise user of 5G networks. For a brief overview of some of the concepts we'll talk about today, and in keeping up with RSA's model of educate, learn, and apply, I want to provide a background on the advent of 5G, how we're using it today, how that's going to change in the future. We'll introduce the architecture and some of the surrounding core philosophy that was baked into 5G from the get-go. We'll present two different conceptual threat models that are not intended by any stretch to be a holistic representation of a threat model, but highlight two diverse areas that are both critically important for us to ensure that we're building holistic monitoring strategies as we implement these capabilities into our networks. And we'll talk about how we can approach some of the existing challenges with current technologies to date. Further then, we'll talk about some existing challenges that we're actively working on tackling where current technologies don't provide a current drop-in solution. Finally, we'll discuss how we can take away some of these concepts and near-term actions on how we can use and apply these capabilities in our current roles, wherever you reside in the enterprise. So to provide a brief background on 5G in general, in a space 5G network, we're increasingly reliant on space-based capabilities, namely space vehicles or satellites. Communication here, terrestrial-based on Earth, is increasingly reliant as we allow those communication capabilities into more and more endpoints and more functions of our daily life. Similar to how IoT has really transitioned the way we do business and the way we execute our daily operations, so too will 5G present a challenge for us. A couple domains where 5G is really being pushed for increased efficiency, increased communications, and otherwise better operations in critical infrastructure. The agriculture industry is a good example. Certainly with emergency response, as we develop mitigation strategies and otherwise response capabilities for natural disasters, 5G is certainly an enabling capability there. Everyone's well aware of the advent of autonomous vehicles and how 5G can bring low latency communications into self-driving cars, or looking at increased mobility in urban environments, potentially with UAS as an example in the future. And as we're all well aware, how IoT has really changed the way we do work in the enterprise or how we do things at home. 5G will continuously push the extent of how those increased communication capabilities are allowing functionality to further the edge, if you will, to our endpoint devices. There are three primary facets of 5G that we'll talk through. And the bottom of the figure here, these are the end users, generally referred to as UE or user equipment. A good example of this is the iPhone that we all carry around on a daily basis. Other examples here include planes, trains, automobiles. As we are increasing the communication ability, so too does that connectedness and allowing 5G go directly to the device rather than through some federated network capability in the enterprise as a whole. As we move up in this image, the kind of 5G network is really broken down into two separate capabilities. The first is what is referred to as G-Node B. And this can be identified as really the gateway into the 5G core, which is really where the 5G network components live, if you will. G-Node B is really just a set of relay capability. So my iPhone as an endpoint can connect to either a terrestrial-based tower, and that communication gets relayed into the 5G core, potentially a terrestrial-based 5G core also, or my endpoint may directly communicate with the G-Node B satellite, which then gets relayed into a core from a wireless perspective, a radio access network. Then the 5G core at the top of this diagram is really where all of the 5G network components live. Two of the core facets of 5G are the premise that it's based on software-defined networking, as well as network function virtualization. And while we have proven the utility over the past decade of these capabilities for increased efficiency, better operations, reduced maintenance, what it does is also presents unique challenges that we need to consider as we seek to monitor these networks. The entire premise of network function virtualization allows for decentralized and decoupling software functions from the innate hardware that they traditionally have been relied on. So now I can deploy potentially one function on-prem and use cloud capabilities or partner sites to host additional capabilities. We lose sometimes visibility into where those functions are decentralized to. And it's important for us, as we're trying to monitor where these data flows are ultimately residing, it's important for us to be sure we understand where those functions live. Why we should care about this advent and this increased 5G use is that, again, as we become increasingly reliant and as satellites increase our terrestrial coverage, if you will, allowing 5G to go to the edge, it's imperative that we build security into the user equipment, the communication profiles we use, as well as all of the infrastructure that really supports 5G communications at the end of the day. It's not simply a set it and put it into orbit, but from a monitoring perspective, it's important that we understand the implications of those controls. Have they been actually implemented appropriately? And do they provide the security and or visibility that we expect them to? And finally, it's no secret in cybersecurity that it's not a question of if, but when cybersecurity incidents will happen. In the face of an incident, response and recovery is critically reliant on monitoring capabilities. That is, getting insight to responders from either a malicious act or otherwise a non-malicious environmental issue. Having monitoring that provides data to responders is imperative for quick mitigation and restoration of services. I'll present the first concept of the threat model here, but I want to provide a little background on the figure that's described. The figure that we see here is from the 3GPP spec, a high-level system architecture. And it's not important to understand every single acronym here, but at a high level, this depicts the different microservices that comprise the 5G core. The UE box is user equipment that we talked about prior in the bottom left. And the attack scenario we'll talk through here from a threat perspective is a traditional or well-known understood attack vector where the adversary is going to directly attack the link between user equipment and the 5G network itself. In this case, the user equipment is connecting to a space vehicle relay. The adversary can directly attack that link. And if unencrypted, the adversary can either spoof, sniff the traffic, or otherwise try and gain access to the user equipment itself, or moving right into the space vehicle and further compromise or otherwise interact with services in the 5G core itself. One thing I do want to call out at this point is that it's not necessarily an appropriate representation to just say there are 4G networks and there are 5G networks. A more accurate representation is really viewing that as a spectrum. And why that's important is that as we are updating or increasing the capability from 4G or LTE networks into 5G capabilities, oftentimes it's not a single light switch where it's flipped over directly. There are certainly instances where standalone or SA 5G architectures are built, but more often what we're seeing are NSA or non-standalone architectures. That is, we're upgrading pieces of our 4G or LTE infrastructure, and increasing the capacity or functionality of 5G. Why that's important to understand is that legacy attack vectors may be carried over as we're implementing new 5G functionality, may be carried over from our existing 4G or LTE infrastructure. It's important to understand then that if we haven't necessarily flipped over all the capabilities required for some of the new 5G security features, and there's a whole suite of security features to be added, not all of those are going to be usable on day one when we start with a new 5G network. So it's important to understand that some of the baggage we're bringing may indeed still present challenge for us in vulnerabilities or otherwise attack vectors from how we execute networks today. In this case, the adversary is directly affecting or otherwise attacking the 5G network itself. So it's imperative that monitoring be focused around the links for the satellite operations in order to ensure that appropriate and authorized use from that UE to the satellite is indeed occurring. From a network perspective, that makes a lot of sense. We can monitor that link and see the communications there. But I do want to call out one box on here. It's AMF. The AMF box, accessibility and mobility function, is the first core service that's really used by user equipment once it is gained access into the core. And why that's important to understand is that if we remember the concept that virtualization of these network functions allows for decentralization or potentially us losing track of maybe where these functions are actually being run, it's important that if we're reliant on that AMF function from an endpoint or logging perspective, and that's a critical piece of monitoring for my security operations center, or in order to execute some incident response, I need to know where that function's running and how to appropriately get that data back if I am doing logging on that function. So as we talk about the increased efficiency and the increased capabilities that NFV and otherwise SDN allow for us, so too do the challenges exist for implementing an effective and holistic monitoring strategy. In this case, we really need to know where all of those functions are indeed running. The second concept we'll talk through is not necessarily on the 5G network itself, but on the supporting infrastructure. And this, the threat concept that we'll talk through, the adversary isn't directly touching the 5G network, could potentially be downstream effects to it, certainly. But what we're really interested in is the supporting C2 infrastructure on the space vehicles themselves. When we talked about the first concept for threat model 1 in the 5G network, there are two primary data planes that the adversary can affect. The first being the user plane. That is, if I have my iPhone here and I download a file over a 5G network, that file is being presented over the user plane. There's a second plane in this instance that is referred to as the control plane, in which all of the kind of network optimization or otherwise network routing and mobility tracking capabilities are occurring, generally unbeknownst to the user at the end of the day. Both of those data planes are in context for the concept of threat model 1. In this case, we're attacking a separate data plane altogether. That is the data plane that is reliant or responsible for maintaining satellite operations. The satellite itself does certainly contain an ingress into the 5G network, but there's a secondary network that's important to consider from a space operations perspective. And this is the command and control network that's used in real time to keep satellites in orbit and to collect telemetry on health status or otherwise diagnostic data. In this case, an adversary interested in affecting the space operations themselves can attack through a space C2 center. Oftentimes, this is part of the ground segment for space control, and being able to issue potentially spurious satellite control actions can certainly directly affect users that are reliant on real-time communications to that satellite. If a low latency application is reliant and has locked with or has a communication flow directly with that satellite, modifying the orbit or otherwise orientation certainly has drastic impact on that communication flow. We'll talk a little bit more in detail later on, but it's also important to understand that while these two networks are generally isolated, it's important for us to validate that the adversary that's affecting the control network for the satellite itself may or may not be able to pivot over to the data plane. We'll talk about some of the controls and considerations a bit later on. So understanding that, we present a reference architecture just to kind of put on the map what are some of the core components that we need to consider from a holistic monitoring perspective. In this use case, we'll talk through a satellite operator who's providing 5G network services. The assets box in the bottom here contain some of the different assets that we effectively would want visibility into in order to pipe those into an integrated SIEM, if you will, or otherwise common operating picture of what cybersecurity looks like. Some examples of that data include, as we mentioned, the space vehicle itself, the satellite. There's a whole host of data around the RF spectrum that we would want to understand. If somebody's trying to deny or degrade our signal or inject directly from an RF perspective into our communications, that's all information that we would want to pull from the satellite domain, if you will. Front-end processors are generally communication capabilities that translates and allow for operators on ground to speak with ground-based antenna in order to communicate with satellites. So logs on potentially data streams or otherwise anomalous capabilities or occurrences on the front-end processor are important for logging capability there. And as we move more into then the ground control network itself, oftentimes we see more traditional IT capabilities, Windows servers, commodity Linux servers. Certainly within satellite networks, there are commodity hardware and software components, and we would certainly want to be able to build monitoring capabilities to those specific technologies. But there is a whole host of oftentimes standard capabilities that we can leverage today to get good insight. As with normal enterprise today, mobile and cloud often do provide some kind of role in satellite operator networks as well. As we move up from assets, it's important to understand that we tangibly need to get all of these data flows, these logs, these network communications, for instance, into some centralized integration piece. For the use case described here, the Elastic Stack is often used as a common integration and otherwise analytic platform. Dashboards created in Kibana can show some of these integrated data sets as they are combined into the Elastic backend. It's important to understand what sensors or what type of tooling we can leverage across all of these different assets and data sources to effectively integrate so we can coordinate and otherwise correlate these data sources. We talked about traditional IT capabilities, some more standard Linux or Windows servers, for instance. We have well-defined tooling and we have well-defined formats. Oftentimes we can drop and drag and drop a parser in or otherwise a connector to get some immediate value out of that. As we move more into the bespoke hardware or software that is generally present in satellite operations networks, for instance, from a front-end processor or from an RF spectrum monitoring machine, we have less ability to just kind of drag and drop in a generic solution. Oftentimes, the tooling available is not nearly as readily available as some of these other more standardized capabilities. So that's a large challenge when we're thinking about how do we get information from those assets? What is the required sensoring or tooling that I need to potentially build or customize in order to get that common operating picture from the integration perspective? So what's clear across, just identifying a couple of the different asset classes here is that it's imperative for us to monitor across the full spectrum. That is network traffic flows, seeing the commands, seeing the telemetry, but also getting endpoint data from Windows servers and potentially correlating those for increased visibility and increased operational knowledge across the mission. Everything we've talked about to this point from dashboard on down in the picture is under the purview of the satellite operator. The final concept I'll introduce is what happens external to that 5G provider. This is where the concept of an ISAC, or an Information Sharing and Analysis Center, comes into play. So an ISAC is a sector-specific information sharing center. They're nonprofits, member-driven organizations, and generally they are comprised of entities in the commercial industry. This is important, especially in space, as we're seeing the advent of increased commercialization and less public utility in space. It's really important that the ISAC represents an appropriate body of those players that are actually present in the industry. The real intent is to help facilitate information sharing across all of those stakeholders, and a key facet of that is increasing the collaboration between government and industry partners. The Space ISAC itself really serves as a single point source for data and otherwise information around the security and threats to space assets. Provide information on all threats. Certainly cybersecurity is a paramount consideration of that, but we really look to the Space ISAC to be that designated body that has all of the information around threats to the space sector. As a member of a Space ISAC, you're not only contributing to the collective benefit of the entire space domain by the information that you contribute or otherwise share to the ISAC, but one of the benefits then is being a user of that information that is analyzed. Specifically for the space domain, we're dealing with generally increased timelines, increased distances. There are a lot of unique challenges, and oftentimes early warning is a very critical consideration. So the earlier that I can be in my mission, the earlier that I can be tipped off to something potentially going wrong or something that I should really try and head off as early as possible, I can really potentially reduce the mission impact. So having a federated pipe and an immediate communication channel to easily and efficiently transfer information that the ISAC provides is a critically important enabling factor for commercial entities in this space. Membership is generally open to anyone interested in the security of the sector-specific ISAC that you're working with. So I want to come back to what we talked about with a certain set of assets, that is the space vehicle. With the rest of the assets that we talked about from a reference architecture perspective, we generally have a pretty good handle on how we can pull logs, how we can otherwise get logs or network traffic appropriately parsed, appropriately formatted, and integrated into some standard IT cybersecurity stacks. The barrier to entry, however, is significantly higher when we're talking about space vehicle communications. If we revisit the point we talked about with the first threat model, the space vehicle itself really is providing two different sets of network communications. One is the 5G network itself, in this case providing multiple G-Node B entry points to the 5G core backbone. And the second is represented in the bottom of the image here. From a command and telemetry perspective, that space vehicle is on the network pulling commands in real time, as well as feeding down telemetry and diagnostic information to space operators. That's important consideration. From a security perspective, there are a whole host of considerations and controls that are generally put in place to isolate those two networks. Certainly what we want to do with monitoring is ensure the validity of those controls and make sure that the controls are not either bypassed, compromised, or just straight up ineffective in implementation. But the secondary consideration around that is if these networks are effectively isolated and we treat that as such, this increases the complexity of my monitoring infrastructure. Not only do I want to be able to monitor what's occurring on the 5G network itself, but I also want to capture information on the command and telemetry data. So really what that does, it puts the burden on the operators themselves to correlate two different sets of information. Oftentimes we can certainly timestamp the data. Once we integrate that, we can correlate the information that way. But an important physical consideration that needs to be thought of too is that as satellites are orbiting, there's generally intermittent communication with ground stations. oftentimes the satellites used for 5G networks are in orbit and not geostationary. And that's important consideration that I'm not going to have necessarily 24/7 eyes on my satellite. Even if I did, we need to consider the bandwidth constraints. Certainly SWaP-C is an important consideration with space vehicle construction, and bandwidth constraints are often quite limited over the current command and telemetry link. So the takeaway here is that this provides a challenge for operators to correlate those two data sets, both from a collect the data first, but then what do I do and how do I effectively integrate those two data sets into my common operating picture for cybersecurity implications. Future work here would certainly benefit the ease and the integrability of these two data sets into more common cybersecurity tools like a Splunk or an Elk Stack, for instance. So moving beyond, I want to talk about responsibility for 5G security. Certainly, it follows that everyone that has a stake in 5G inherently has some type of responsibility for the security. Government certainly plays a role in developing policy to ensure that we can secure these systems and that we can enable security within these systems. Just like the FAA does for aircraft, for airworthiness, it's important that the government would play a role to ensure trusted access as well as fair use and acceptable use of these systems moving forward. Space, however, presents a unique challenge in that it is an international domain. So as nations are defining policies for what acceptable use looks like, it's important that we consider that those policies ultimately need to be welcomed and accepted by or otherwise interface with other nations to form an appropriate international policy. Moving on to space system operators, they have a piece of the responsibility pie here that is ensuring command and control of their space vehicles are accessed and maintained by authorized individuals. Ensuring that the security of that control network is paramount really has a important effect to the availability and the integrity of the 5G network itself. As 5G is inherently reliant on space-based capabilities, so too is it on space system operators to maintain the availability of those space-based capabilities. 5G network operators then, they share the responsibility by ensuring secure communication between the ground and space, as well as capabilities within the 5G core. If we remember back to the kind of spectrum of 4G LTE networks into 5G networks, it's important for network operators to be aware of and understand that if we're not operating in a standalone capability, some of the 5G security features may not be available to end users and may not be available for increased visibility. The baggage that we're potentially carrying from current 4G or LTE networks must be well understood as we're integrating and moving more towards 5G only networks. And finally, to talk about the consumers, really the end user. These are the folks that, again, I download a file on my iPhone. I am the end user operating that user equipment. End users should certainly be concerned with privacy implications as we are allowing 5G capabilities and more functionality into our daily lives. It's important that we understand what the privacy implications are. Oftentimes, security is an enabling factor for privacy, certainly with different intent at the end of the day, but both are core facets. And from a personal perspective, it's important to enable the user to make an informed and ideally a risk-informed decision by knowing how they are allowing 5G into their lives and what potential risks they might be allowing by doing that. Certainly, as we move 5G capabilities into more critical applications, the efficiency gains of moving towards autonomous vehicles, for instance, or robotic manufacturing, where some of these applications rely on low latency or potentially high bandwidth comms, we should be aware of the criticality of the functions that we're allowing 5G to have access to. And it's important that we weigh that risk versus reward ratio and consider the implications of 5G security and how they may affect some of our safety critical operations and functions. So moving forward, some immediate actions we can take. If you're a space operator or a 5G network operator, for instance, devoting resources and identifying really where out-of-band monitoring solutions would not only enhance, but also integrate with your current situational awareness picture. Building additional capabilities and integrating those into a more common operating picture for a holistic monitoring solution is a very important consideration. Certainly, considering the participation in the space ISAC as both a contributor to the space domain as a whole, as well as a user of the data feeds that the ISAC provides, is an important consideration. As more members join ISACs in general, so too does the common strength of the information that we're able to share. Increased visibility is really the concept that allows for more efficient and more effective information sharing within the domain. Then a little bit further off is considering how, once we've built those capabilities, how do we use that information? How do we use that monitoring capability that we've implemented in order to identify certainly baselines on what network assets and what network communications are occurring, and ultimately being able to track down what communications should not be occurring, or being able to more acutely define how behaviors are occurring on trusted or potentially untrusted devices on the network. I do want to make sure that it's important for users to take away that this is not just a challenge presented to space operators or to 5G network operators. As 5G is increasing to endpoint devices in our homes and in our workplaces, it's important that we understand our reliance today and how that reliance will change over the next 3, 6, 12 months in the future, and how our business operations will change in order to be dependent on those 5G services. From that perspective, similar to the paradigm shift we saw with cloud computing, this is going to change the way we need to do cybersecurity defense and otherwise cybersecurity visibility into our operations. So being able to identify business objectives or otherwise system requirements where 5G is the infrastructure of choice is an important consideration that everyone can take back to their personal life as well as the enterprise in which they work. In wrapping up, the two threat models we presented are intended to provide specific insight into two different, very diverse attack paths that we should certainly consider as core tenets of a holistic monitoring strategy for 5G moving forward. Being able to use what we talked about here in identifying potential use cases for increased monitoring and potentially how external feeds such as what Space ISAC provides is an important consideration to think how that can enhance an organization's current situational awareness. And being able to act on that, we should be able to then inform a better out-of-band monitoring strategy that's more holistic to incorporate some of these additional threat vectors that we've talked about. And secondarily, consider feeding back as a contributor to the space domain, as well as a user of space information coming from the ISAC as a consideration. I thank you all for the time and appreciate the ability to speak with you all today. And I really look forward to addressing the challenges we talked about with the community as a whole moving forward here. Thank you very much.